Today we're going to do the second part of 7-4, so it's going to be applying properties of similar triangles, and this is continued. So before we actually begin on the new stuff, recall theorem 7-4-1, which was the triangle proportionality theorem. Now what this theorem says was that if we are given a triangle, it doesn't matter what triangle again we have, but if we're given a triangle, let's go ahead and call this A, B, C. Now what this theorem says is that if we were to take a parallel line, let's just go right here, we know that it's going to be parallel to our base of BC, and it creates points of X and Y at the intersections. Now what this theorem says is that AX over XB will be equal to AY over YC. In other words, it cuts the side, it cuts the left side and the right side proportionally. So AX over XB is equal to AY over YC. Now we're going to move on to 7-4, or rather the second part of 7-4, and we're going to move on to a corollary. Now this corollary is very, very similar, but all we're going to have to do now is no longer think of it in terms of a triangle. Meaning if we were to redraw this shape, almost pulling this side out and pulling this side out here, we can still apply the exact same proportion here, and we'll be able to say that exactly with what our theorem tells us. So we have corollary 7-4-3, which is called the two-transversal proportionality corollary. What it says is that if three or more parallel lines intersect two transversals, then they divide the transversals proportionally. So what that means is that if we need two transversals, meaning just any two lines. Let's just draw one, let's say here, and let's draw one, I don't know, here. So we have our two transversals. Now it tells us that we want three or more parallel lines. So we'll just go ahead and draw three, but let's go ahead and draw horizontal lines, just parallel horizontal lines. 1, 2, 3. We can label these intersections now of A, B, C, D, E, and F. And again, this is just like our triangle proportionality theorem, except obviously we're no longer dealing with a triangle. But it's along the exact same lines because we know all these sides, all of these lines here are parallel. So what exactly does this corollary tell us? Well, it tells us that it divides the transversals, meaning this line there and this diagonal line, it cuts these proportionally. Meaning that we could say this little segment here, AC, so we know that AC over CE, so the left side over the other part of the left side, is going to be equal to the top part of the right side, which is BD, over DF. And that's all this theorem or this corollary tells us, is that if we have these transversals cut by parallel lines, then the ratio of the little segments are going to be equal to each other. Now we have an example. It says that a freeway is supported by vertical parallel pillars as shown. So we have our freeway, and it's, of course it's just a diagram, and then we have our parallel pillars that are vertical, and we want to find AQ. So we want to find the length of this little segment right here. So let's go ahead and mark our diagram showing that these guys are parallel. And now what we notice is that, well, we have two transversals, meaning just two lines. Well, they do cross other lines, but we have three parallel lines, and that's exactly the criteria we need for the corollary we just talked about. We have our three parallel lines, and they cut two transversals. So what we know is that the transversals are cut proportionally. As our corollary tells us, and that is corollary 7-4-3, tells us that we can set up a proportion of the transversals. So we know that PA over, well, I did this distance here of the top one over AQ will be equal to SB over BR. And that is what our corollary would tell us. Now we just need to start plugging in some values. So we know that we have 32 over, well, we don't know what AQ is, so let's leave that as AQ, is equal to 30 over 24. And now we just need to simply cross multiply. Cross multiplying would give us about, so AQ should be about 25.6 yards. And that's just solving a proportion as you know how to do by now. We have one more theorem in this section, and it's theorem 7-4-4. It's slightly different in that we're no longer dealing with the parallel lines, but we're still dealing with proportions. So an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. Now that's quite a mouthful, but if we just read it piece by piece, it's fairly easy to understand. So we have our triangle, let's call it ABC. Now, what we need is an angle bisector of a triangle. So meaning that it's an angle bisector, it's a segment that goes through an angle and it cuts an angle in half. So let's go ahead and cut angle A in half. So we want a bisector, so meaning it's going to cut through just like this. And we know it's a bisector, so therefore we can say that those two angles are going to be congruent. We can call this, let's just call it X, that intersection. Okay, so an angle bisector of a triangle, we've got that, divides the opposite side. Well, our angle was A, so our opposite side is BC. So it's saying it cuts BC into two segments whose lengths are proportional, so the two segments are BX and XC, proportional to the lengths of the other two sides, meaning AB and AC. So what this theorem tells us is that, again, this whole side, BC, is cut into two segments that are proportional. So you have BX over XC. You notice you had BX, XC. That's what formed BC. And that is proportional to what? Proportional to the lengths of the other two sides. Meaning AB over AC, as we had our other two sides of the triangle. And that's all that this theorem is saying. So again, it is quite a mouthful, but it is not very difficult to understand if you go piece by piece. All right, now we've got an example to find AC and DC. So AC is over here, and DC is over here. So we're going to find the length of those guys. Now looking at this, I do notice that we do have some different measurements going around here. But you also need to recognize right here, these two red marks means that those angles are congruent. Meaning that AD is an angle bisector. So because of the angle bisector, we can use our new theorem, which is theorem 7-4-4. So the key is because we have angle bisectors right there. All right, now that what that theorem tells us is that the opposite side, BC, is going to be cut proportionally. So 4.5 over y over 2 is equal to, well, we know it's going to be equal to 8 over y minus 2. And those are because it's the other sides. Now, be careful. This is just a quick reminder. Be careful about 8 over y minus 2, rather y minus 2 over 8. And I say that it has to be 8 because 4.5 is the one on top. Meaning how 4.5 and 8 are kind of on the same side of the triangle. So is y minus 2 and y over 2. That's how I know which order to go in. So the 4.5 should be on top with 8. And y minus 2 should be on bottom with y over 2 should be on the bottom with y minus 2. Anyway, solving this, you might be scared right here. You might be scared to have a fraction and a fraction. Well, now I'm not too concerned because I know I'm going to cross multiply. I know that I'm going to multiply y minus 2 times 4.5 is equal to y over 2 times 8. Be sure here to multiply all the way throughout. So what we see is that it's 4.5 y minus, use a calculator, you find it's 9. And this is equal to simply 4y. Getting the y's on one side, I see we get 0.5y is equal to 9, because I moved the 9 over. And therefore, y is equal to 18. Now, some people might have wanted to say 4.5 at this point. Be sure you're dividing by 0.5. It's 9 divided by 0.5, which is 18. Now, we're not quite done because now we need to find AC. So AC is equal to y minus 2. Well, y is 18, so therefore AC is simply 16. Same with DC. We have y over 2, which gives us 18 over 2, and therefore DC is a length of 9. And now we are all finished. So be very careful setting up your proportion, but that's all we had to do. We recognized we have angle bisector here, so we can set up a proportion and just simply cross multiply from there.